Okay, so today we're going to continue our study of introductory number theory. So you need to recall a few definitions for today's lecture, in particular the definition of divisibility. So over here. Okay, so definition. This is from last time, by the way. So let A and B be integers. Okay. Then A divides B. Written A bar B if there exists an integer k so that B is equal to A times k. Okay, so this is from last time. Okay. Now, next definition, which relies on this definition. Okay, so let A and B be integers. Oh, by the way, you have to say A is non-zero. All right, so let A and B be integers with M being some positive integer. Okay, so then we say that A is congruent to B modulo M if M divides A minus B. And we write A congruent to B mod. Okay. So this is the definition of congruent. N is called the modulus here. And this is not an equal sign or anything like that. This is literally a definition. This holds whenever that holds. Okay. That's all that's saying. This is saying that. That's it. Okay. So for today's lecture, you're definitely going to want to have that written down. And then also, you are going to want to have this theorem written down. And this theorem is called the division operator. Okay, so it states that if, say, A is an integer and D is a positive integer, then there exists really important, there exists unique integers Q and R 0 less than or equal to R less than or equal to D, so that A is equal to B times Q plus R. And we're not going to prove this today, forever involved. We're going to prove this maybe a week or so. But just for now, take it as is. It's a true theorem, division algorithm. And all of you are probably familiar with this, this statement. So here, D is called a divisor. Q is called a quotient. And there's special notation for the quotient. The notation, so Q is equal to A div D. So separate there, div D. And then here R is called the remainder. Okay, and there's special notation for that. R is said to be equal to A mod D. Okay, so for an example of this theorem, take something like I don't know. So say maybe like A is equal to 13, D is equal to 5 or something. Then this theorem states that there's unique integers that satisfy this formula. So here, what would Q be? Q would be equal to 2, and then R would be equal to 30. And then notice that R is strictly less than the divisor D, and it's greater than or equal to. Okay. So those are the unique integers that satisfy this. So, but there are other integers that satisfy this equality. For example, if Q is 1, be 5 times 1, right? Plus 7, right? No, sorry, 8. But then 8 would not be less than the divisor, so that wouldn't work. It must be the case that the remainder is strictly less than the divisor. And when that's the case, you have unique Q and R that satisfy this theorem. Right? So these two definitions in this theorem, we're going to use to prove an if and only if statement. Okay? So take a moment to write those down. Make sure that you have that the remainder is simply denoted by A mod D. So when the remainder when A is divided by D is the same thing as saying A mod D. Okay. Okay, so I'll give you another second to write that down. And we're going to use all of this in the next proof. Okay. All right, so hopefully everyone has it written down. Okay, let's look at this. this theorem now. Theorem. All right. So if A and B are integers and M is a positive integer, then A is congruent to B mod M, modulus M, if and only if A mod M is equal to B mod M. Okay, so these are equivalent statements. So this is saying that the remainder when A is divided by M is equal to the remainder when B is divided by M. They equal if and only if A minus B is divisible by M. Okay, so proof. You got to have those definitions next to you and ready to go for these proofs. So first suppose let's say that A is congruent to B modulus M. Okay. So then, by definition, there exists, I know, in my definition, what do we know? We know that M divides A minus B. Okay? All that's saying is that if this congruence holds, then we know that M divides the difference. But if M divides the difference, then again, by definition, there exists some integer k so that A minus B is equal to M times K. So that A minus B is equal to M times K. That's just, that follows from that definition, which is, that follows from that definition. Okay, now we're going to use the division algorithm. So by the division algorithm, there exists unique, say, quotient Q and R, or quotient Q and remainder R, that are integers, with 0 less than or equal R, which is less than the divisor M. That's just the divisor. So that A is equal to M times the quotient plus the remainder. And then note that R is A mod M, the remainder when A is divided by M. Okay. So now, if we substitute this A into this equation, so we have to make something like hence, we have A minus B is equal to N times K, but then A is really M times Q plus R times B is equal to N times K. Okay, so then moving around things, we see that M times Q minus N times K plus R is equal to B, or in other words, M times Q minus K plus R is equal to B. Okay? Now, since Q minus K and R are integers with 0 less than or equal to R, which is less than the divisor M, right? That property comes from here, right? R is strictly less than M. So since R is less than M, Q minus K is the unique integer together with R that satisfies the division algorithm applied to B. So the division algorithm states that Q minus K equals, what is it, B div the divisor, and R is equal to B mod M. Hence, A mod M is equal to B mod M. Because R was the remainder here, right? This R right here, that's this right here. So then here we have so this is the divisor. And then since R is strictly less than the divisor and is greater than 0, that's the unique quotient when B is divided by M. So that means that that's the unique remainder when B is divided by M. So we've shown that that remainder is the same as that, so these equal each other. Okay. So that proves one direction of the if-and-only statement. Now we have to prove the other direction. Okay. So typically I would write an indent right here and I'd say conversely, and then prove it. So I'm going to have to erase to have more room. So then conversely, suppose that the remainder is equal. Suppose that A mod M is equal to B mod. Now I want to show that that congruence holds up there. So we're going to use the division algorithm. So by the division algorithm, there exists integers, say q1, q2, r1, r2, with 0 less than or equal to r1, which is less than m, and 0 less than or equal to r2, which is less than m, so that A is equal to m times q1 plus r1, and B is equal to m times q2 plus r2. Oh, I didn't say, so inside, so like right here, I should have said unique integers. That's important. So there's this unique integers q1, q2, r1, and r2 that satisfy this by the division algorithm. Okay. So now I want to look at showing that m divides a minus b. So, oh, I should probably note, we suppose that a mod m is equal to b mod m, i.e. the remainders are the same. So I should probably say something like note that r1 is equal to r2. Okay. So maybe something like hence, if we look at a minus b now, that's equal to m times q1 plus r1 minus m times q2 plus r2. Like that's a and that's b by the division algorithm. So then notice that this is the same thing as saying, so just grouping these together, m times q1 minus m times q2, and then plus r1 minus r2. Now, r1 is equal to r2, so that's just 0. And we're left with this piece here, which we can then factor out of m. Like that. And then, since q1 minus q2 is an integer, m divides a minus b by definition. So since m divides a minus b, so it follows that a is congruent to b modulo m. And that finishes the proof. Okay. So this is a biconditional proof. It's an if and only if statement. And we had to make use of the division algorithm several times. And we had to make use of definitions of divisibility and of congruence. So as you can see, things are starting to stack more and more, and you really need to have these definitions and these main theorems down on note cards next to you so that you can use them. Okay? So, seems this level of proof is probably something that you would see in like in modern algebra 1 course. Maybe the first part of a senior level modern algebra course, you would see a proof that looks like this. Modern algebra and divisibility and number theory kind of overlap at the undergrad level. So these types of proofs are getting you ready for going into those types of courses. Okay. Okay, so let's look at another theorem. So let me just pick one randomly out of the textbook. Okay. Theorem. So let M be some positive integer. Okay. It says if A is congruent to B modulo M and C is congruent to D modulo M, then say A times C is congruent to B times D modulo M. Okay. So we should be able to do this just straightforward direct proof using the definitions. Okay, so we'll do this with a direct proof. And again, for you guys, it helps to have your scratch work on one side. I think that this is straightforward enough that if we just apply the definitions and write out the proof, we should be able to get to the conclusion. So we're going to say suppose the hypothesis, so suppose A is congruent to B modulo M, and C is congruent to D modulo M. Okay. So then we just apply the definition. So then by definition, we have that M divides A minus B, and M divides C minus D. That's just applying the definition there and then applying the definition there. Okay. So then we have the definition of divisibility. So you can say something like, then, again by definition, there exists integers k1 and k2 so that A minus B is equal to m times k1, and c minus d is equal to m times k2. Okay, let's just applying the definition again. So we want to look at a times c, b times d. So maybe I can rearrange these equations. So note that a is equal to m times k1 plus b, and c is equal to m times k2 plus d. So I know what a and c look like. Now I'm going to multiply them and just see what happens. So maybe something like hence a times c is equal to m times k1 plus b times m times k2 plus d. Okay? So then if we just expand this out, what do we get? So m squared times k1 times k2 plus d times m times k1 plus b times m times k2 plus b times d. Okay? So then we have that b times d term and a times c there, and we want to show that m divides that difference. So I can move that over and I see that ac minus b times d is equal to this sum here. Okay. So I want to show that this is a multiple of m. So I want to prove the conclusion here. And I see that there is indeed a factor of m all the way through. So what I'm going to notice is that a times c minus b times d is equal to m times k1 times k2 plus d times k1 plus b times k2. Okay, there. So that right there, so I can just say since that term m times k1 times k2 plus b times k1 plus b times k2, since that is an integer, m divides that difference. M divides ac minus bd. Hence, we can say that a times c is congruent to b times d modulo m. Yeah. Okay. So again, this one is a little bit easier than the previous theorem. You didn't have to call on any technical theorems to prove this. You just really had to apply the definition and then apply another definition look at what you want to show. You want to show A times C. So I just solve for A, solve for C, and multiply them. And then I want to say, oh, I want to show that the M divides the difference. So I move that over and I see that there's a common factor of M, multiplying some integer, which means that M does divide the difference, which means that the congruence holds. Okay? So the previous theorem, I put it like a difficulty level of like a 7 or 8 for you out of 1 out of 10. This we have a difficulty level of probably like a 4 or something like that. Okay. Okay, so that will be it for my example proofs today. I'm going to leave you with some practice problems to try. So under these same conditions, prove that A plus C is congruent to B plus D modulo M. Okay. So prove that. Then maybe say that'll be it for now. Just try to prove that one, and I'll see if I can find some other problems to pose for you. Okay. Okay. So that will be it for today. Any questions about these proofs? All right. Well, everyone stay safe, and I will see everyone on Thursday.